I did want to sort of remind people about the Medical Intelligence Society. If you don't know about it already, certainly we can send you the link. If you just go to misociety.org, the website will give you the information. It is every month. It's the, I think, second Tuesday. Make sure I've got that correct. Yes, the second Tuesday of the month. It would be at 4 o'clock Central, 5 o'clock Eastern. It's a 2-hour session. The first hour is data science and AI, primarily with one journal article and a speaker. The second hour is medical innovations, often presented by medical students and others. And also it really is international. There is a speaker, but this is where you'll hear about what's new with medical technology and devices and a lot of things you otherwise would not hear about. And then there's kind of a social, not hour, but a few minutes where you can network with people. But I don't know of anything that's even similar in medicine so I think for people interested in data science, AI, and innovation, it's really an excellent opportunity. Okay, I think in the email, at least I hope I did, the newest version of Orange is version 3.33, and they, lo and behold, generated a new version just so they could have a precision recall curve, which I requested. So I feel good that they, took that seriously and now have offer that. And I'll demonstrate that when we get down to models and whatnot. But 3.33 is the most recent, and I think that's the only addition. Now, David and I have worked hard to modify the book, including the title, the cover, a bunch of other things. We put all supervised learning in one chapter, all unsupervised learning in one chapter. We also have cheat sheets, which means that there are a lot of data science cheat sheets that are tips and almost like a glossary in a way. And then for each chapter, we opted to use AI generated art. This came from DALL-E. You have to put in a bunch of different types of text to get images, but so that's in there. Instead of having a chapter entitled Putting It All Together, we decided to have at the end of every chapter a putting it together summary, in other words. So we changed that to a summary for every chapter, and that'll include data exercises for everybody as well. Now, as I said before, and Anthony has pointed out too, this is a little bit like building an airplane while you're flying it. So we ask you to be patient. There are going to be new versions. I sent everybody the most polished version of chapter 1 I could. But again, it's likely to change. The other thing, and I can put this either in the chat or I can send it to everybody, I have created a data repository on GitHub for classification regression. There's roughly 10 classification data sets and 10 regression data sets that we'll use. And you can download, those are publicly available. You don't have to log on, so it makes it fairly easy. I don't want to, I've had so much technology problems this morning, I'm reluctant to get out of here and try to get the URL, so I may just send that to everybody via email. That would be, for me, easier if I can. Let me see, is anybody, I haven't had a chance to look at everybody attending. Is anybody new today that has not joined this US workshop? The names I see so far look familiar to me.
Hi, Bob. I mean, I've always consulted.
Okay, Arif, were you here last time? I guess you were not.
Your expertise in the past, but that I was not. But yeah, my name is Arif Rana. Just hello everyone. I actually am a faculty at SUNY Polytechnic Institute, but I've always valued Bob and David Petrishkov's expertise and input. So I really look forward to learning from you and all of other attendees.
Okay, we're honored to have you here. So where we left off more or less the last time is the section on what the data scientists do. And I think most people have a feel for it. It's been confirmed in industry that these are the talents that are requested, and they obviously are based on largely higher math and statistics, programming ability, particularly in Python, but also SQL. They also have experience with database management. They're good at creating predictive models, and also they're very used to dealing with machine learning, creating predictive models, using that and artificial intelligence. And lastly, they have soft skills. Now, I think since the last time I added this diagram, this shows the breakdown of what a data scientist does. And this is from a 2022 survey. And that's why I included it, because it's more current than anything else I could find. But it confirms what we've said all along, that a data scientist spends a majority of their time, the data preparation, data cleaning, if you will, reporting and presentation, visualization, and only 9% in model selection, 9% in model training, and 16% with the other, like deployment. So it just is a little bit more granular, but it really confirms what we've said all along. The other thing is I added this table that goes over some of the other job descriptions. Please keep in mind that this is evolving, meaning I keep seeing new terms, machine learning ops engineer, for instance, a whole bunch of them. So I'm not going to get too wrapped around the axle about these terms, except to say that traditionally in a large healthcare system, the data engineer goes in and builds a data pipeline from, say, a data warehouse to some either web-based or some type of machine learning model, usually, or AI, to create this. And then the data scientist comes in, uses the data, creates a model, and is there to present and is very involved with the rest of it. But you can see there are other job descriptions, like a data architect, as just an example of some of the new titles. Here's a machine learning scientist. I personally have not met a machine learning scientist. They've all been data scientists, but again, here are these terms that you should be aware of, the tremendous overlap, and I suspect that they'll merge. Now, why learn data scientist? I would argue there's clearly two reasons for most people. One of them is machine learning and AI is here. It's pretty pervasive. Some of it's new. It's still in development, if you will, but it's here. It's not going away. And second of all, how are we going to get people to interpret recent literature without knowing the basics? I've said in some of my other PowerPoint lectures that even understanding something as mundane as a confusion matrix is critical. Often they're stuck in the supplemental file. They're hidden because the authors may only want to report accuracy or only report sensitivity, but don't report specificity, or vice versa, you name it. But if the confusion matrix is there, you on your own can calculate all of that, and you can much more intelligently interpret an article about predictive analytics because of that. Now, challenges, there are many challenges. One, of course, is there are not enough people probably to teach it in the healthcare domain, people that are comfortable with the healthcare domain and data science at the same time. They tend to fall in one camp or the other. There are other challenges in terms of like learning programming, which is ideal, but not practical for the average clinician. It takes too long to get proficient at it. Also, we're still finding their way a little bit on how to do an optimal article, how to publish it, what are the do's and don'ts. More and more, hopefully, the editors will mandate exactly how that article should be. Why did we create this textbook? Fairly obvious, is just trying to make this appeal to a wider audience. We will likely have a chapter here on Lean Six Sigma and how That is an integral to healthcare system. David, you want to say a word about how you view this to be integrated in the book in the future?
Yes. You know, it's interesting because we have an estimated 4 to 5 million trained Lean Six Sigma professionals in the world. And these are all people that understand basic statistics, advanced statistics. Everything they're taught has nothing to do with coding. It's all with software, typically Minitab or Jump or something else. And a lot of them are chomping at the bit to go to the next level. And already, you know, that the world of Lean Six Sigma is all about quality, and there's already publications about quality 4.0 and what's the evolution of Lean Six Sigma. And guess what? It's all about integration of machine learning and predictive analytics. And I've been speaking at Lean Six Sigma conferences for the past 4 years in that topic, just to see exactly how are people getting ready for it. And they're kind of ready for it, but they don't want to go into the world of coding. If there are no coding solutions, they are ready for it. And that's what, you know, Bob and I and others are trying to, you know, offer the world at this point. And then that chapter will deal more with that topic.
Thanks, David. And again, as I've hinted before, the book is progressing nicely thanks to David's contributions. I think it's very readable, and it's always good to have two people scrub a section to make it as good as possible. So I put in here what a faculty need to know. We do hope that this book here soon will be something that can be used by other faculty to teach basic clinical data science, if you will. But we don't have an instructor manual yet. But we have a lot of ideas how to make it better. You will see QR codes throughout the book now that'll take you to either videos we created, Orange created, or StatQuest. And if there are others, we'll include them. But a QR code, the advantage of that is it can be used for an electronic book or a print book. So stay tuned. There'll be more information of what we planned. I mentioned that we had already tried a lot of different programs. David has been an expert with Blue Sky Statistics, which is one of those R-based like JASP, but it's even more sophisticated. That's why the Mayo Clinic, is it the research division, David, that's adopted Blue Sky at Mayo Clinic?
Yeah, they use Jump Pro for the last 20 years, and they threw it out all for the benefit of Blue Sky. After they asked Blue Sky to add, you know, dozens of different features, which they obviously gladly did.
So again, we're not here to promote Orange per se, except to say that we don't know of a decent alternative that does as much as it does. It was, after all, designed for education, no other purpose but education. Now, it can be used, obviously, for a publication. Since it's Python based, it's really no difference between you saying you generated this predictive model in Python versus Orange. It's really one and the same, if you will. So one of the things we may do is when I finish this chapter, go over a little bit of tips before we move on to chapter 2 on data, which is incredibly important. But I wanted to ask, has everybody had an opportunity to download Orange and take a look? Has anybody not gotten that far? You can put that in the chat if you like. I've not looked at any of the chat so far. I see some input. Thanks, Irene.
Oh, yeah, that I was good to just mention.
Okay. But we'll do a little bit. Again, I'm using a Windows computer after 2 Macs failed. So hopefully my navigation will be okay, but we'll go over a few things and I'll ask David to contribute too about some very interesting and probably we would consider unique features that Orange present that other programs do not. I already mentioned the difference between the file widget that has, I think, 6 files already loaded, and then dataset widget that has 65. So that we'll do the same thing to show the simplicity of it. This figure 1.7 takes you through the steps that you always have to begin there. Remember, if you're doing predictive analytics, you need to set the target. You need to change it to decide what it is you're trying to predict. You change that to target and then hit the blue apply button, and that activates it, if you will. And so we may create one of those real quickly here and go over a few things. So I'm just using this. So here is putting it all together section that will be there for every chapter. This will not be quite as long. There won't be a data exercise, but there will be orange exercises in chapter 1 for students. So this is still not completely mature. Let me see if you see my orange screen here. Do you see that?
Yes, we can see it.
Okay. All right, my menu, let me move it to down to the bottom here. One thing you can do, just FYI, if you don't need or want that large menu, you just uncheck expand and it disappears. The reason you don't have to have that is, notice if I just right click, what happens? First thing comes up the file. So you can get by with just right clicking for everything you need if you want. So in the file, again, we can click any one of these. I tend to like the heart disease one for the clinicians at least. But here's where you'll go in if you want to change anything. Like notice this is what we're trying to predict is set as target, but to change it, all you have to do is change it to feature. We'll change it back to target and hit apply. And I now, David, see why your images on a Windows look different than my images on a Mac. That explains it. But then connecting it, I think what we'll do, David, I'm going to go ahead and use that rank thing that David had a real good brainstorm here. Let me do select columns. Let's go ahead and do the rank. Just put RA. Rank widget. And we're going to show you a unique way for model explainability that I did not explain the last time I presented at the Medical Intelligence Conference. And in fact, David, if you want, whoops, let me connect this correctly. Now, why is that not connecting? Isn't this the workflow that we used, David? I mean, we used, let me exchange this and just use
into
random.
Logistic. Okay. Don't ask me why neural network did not work, but the idea is you can't always explain what random forest sees. This is a way to get around that. The select columns, you can go in and be sure you like it. The target is diameter narrowing. You've included all the predictors, although you could take one out. For instance, we know ahead of time that this fasting blood sugar thing contributes nothing. So I'm going to take it out of the model. David, you want to take it from there and just explain the workflow, why we did this? Yeah, why don't you click on the rank while I'm talking here? So yeah, what's interesting here is that we have very quickly, if we want to know, we have some data, we have a target, we have a bunch of predictor values, and we're trying to find out what are the most important factors that we're dealing with here. And the rank widget can actually work by itself, or like Bob showed, he added one of, the machine learning algorithms, random forest. And if you have a look at, let's see if Bob, if I could, can you see my cursor? I don't know if I have.
Yes, we can see the cursor.
Okay, good.
Well, we see Bob's cursor maybe.
Yeah.
Yeah, I don't have control. If you give me screen control, Bob, I could click around a
Let
little bit.
let's see. But it would have to be your orange though. In other words, you can't control my orange.
So on Zoom,
Okay,
Bob, there's an ability to give control to somebody to control your mouse. So
Okay.
then David can click around.
All right, is that under screen sharing somewhere?
Because it's usually the host that has the option, so I can't see what the option
Yeah,
is.
I don't know. David, can you tell me what you want to demonstrate? Maybe
exactly.
the
That's what I was going to suggest. I'll just tell you what the click is. You can see what the rank widget has built into it. You can see in the upper left-hand corner, Bob has checked 2 of the possible 7 what are referred to as scoring methods. These are mathematical scoring methods that'll tell you right out of the chute, just by those 3 widgets, even without the random forest, what are the most important factors that are actually contributing to, this situation here in heart disease. And Bob had 2 of them checked, information gain and information gain ratio. And if you look carefully on the right-hand side, the 3rd column of the kind of the Pareto chart that it shows also the random forest. And what it did, it added that to the 7 because Bob added at the bottom there the random forest widget, and it included that in the analysis. Now, Bob, if you click on the top header of random forest, just click on it, left click on it. Now take your cursor away. Click it away so we could see so what we can see now is it has reprioritized the rank just according to the random forest algorithm. So it'll tell you, what are the most important factors that algorithm is seeing. And so the beauty of this is you can then Bob, you could even just for kicks click 2 more of the scoring methods on the upper left-hand corner, the Gini and the decrease and the Nova. Just check 2 more, check 2 more of those, and then expand the width of that view box that we have in the rank. Just there we are. And we could now see, all right, it didn't, the ANOVA didn't cooperate for whatever reason, and that's okay. So you could uncheck that. But we could then compare it to other analysis types of techniques. And what we want to ideally then come up with is try to find out, do they at least agree in the top 3 or the top 4 or the top 5 factors? And if not, then we could explore that a little bit deeper. So this is a very quick way to find out from a data set without too much, fuss about what are the most important factors.
Thanks. And I would say it's really more interpretable or explainable, if you will, than say SHAP, S-H-A-P. So again, point that out as fairly unique. Also point out, which I think hinted last time, is you do need to be sure that you checked all the packages. These are really Python packages to see if any of them are pending. Looks like it's up to date. Again, the newest is 3.33. Real quickly, let me make a duplicate of this. We'll connect it to, let's say, test and score. And I think, let me see, the newest name is performance, I think. Yeah, performance curve is the, and then we'll use logistic regression maybe. So here is what it, a precision, let's see, wait a minute, set the target to 1. There we go. So this is what I requested that orange add. If this should be normally a mirror image of the receiver operator curve. In other words, if you flip it over, that's what the receiver operator curve looks like. However, if you have an imbalanced data set, which is really common in medicine, This gets squished way down. So I would guess this doesn't calculate the area under the precision recall. I would say this is like 85%. But in the case of one of the imbalanced ones that I put in the textbook, it squished it all the way down and probably about 15%. So this is the curve that you should report if you have class imbalance. You have way more of one class than another. So that's the new feature in there. Are there widgets that anybody has wanted to test or wanted to look at while we're here before we move on to chapter 2? Here is the choices. Again, some of these we've not demonstrated, like getting rid of duplicates is unique. That's one I have not demonstrated, but you can. There are, again, a variety of others. This feature constructor, we have not gone into much detail, may later on do it, but requires some degree of coding or understanding, not Python code, but a type of code, if you will. Imputation we'll get to, and David has expanded that really beautifully in chapter 2. I mean, if nobody has any heartburn or difficulty with the basic workflow here, I'll probably move on. I'll remind you that you also have the ability to label your workflow. You can add arrows so that you can label your own if you happen to want to teach it. Put an arrow in the description and text here. And then obviously, when you're done, if you've created something that you want to keep, you save it as an OWS file, which you can share. You can include that in an email if you want somebody else to upload it and have exactly your workflow, which is, to me, quite a nice feature for education. All right, if nobody wants to see us test drive anything else in Orange at this time.
Bob, there was a question about the GitHub link. You might have just passed it in the references. Somebody is, I didn't have it at my
actually,
fingertips.
if you'll bear with me, since I'm on Chrome, it should only take a second. Let's go ahead. And it may, on this computer, may not recognize me. I don't know. There we go. Although Chrome is Chrome, so it doesn't make any difference which. So this is what you're going to see. So in the classification is like 10 data sets, regression about 10 data sets. So I'll copy this and paste it. Okay, so you should be able to see it. And Anthony had to log off, or no, Flora, I'm sorry. So we appreciate, thanks, Flora. Okay, so that's that. I'm going to go return to the book. Again, this is a AI generated image. I can't remember, I may have put doctor analyzing data or something that generated that. You have to, there is some trial and error just for those people that don't know. You can't just put anything. If you put words like data science, you get gobbledygook, believe it or not. All right, so let's start on the data and data types here and understand that this chapter, like chapter 5, is super important. I mean, I can't overemphasize how much we depend on data. And as John Lee said, data is the new oil, but in medicine, it's crude oil. It needs a lot of distilling and interpretation. And boy, that couldn't be any better said than that. Let's go over this diagram. Dr. Chang had this in his textbook. And I think the idea here would be, to me, I use the analogy of this pyramid as, let's say, an example of data is just the number 10. Information is it's a hemoglobin of 10. Knowledge is, well, hemoglobin of 10, yeah, but this patient has chronic renal failure. And then wisdom is, I'm not doing anything about it. Intelligence may be AI or machine learning, looking at that data for you and saying it falls within normal for a patient with a creatinine of 9. In other words, it is embedded in there between knowledge and wisdom to augment or accelerate your wisdom. So this, again, is a new diagram for Dr. Chang's textbook that I think is important, how intelligence can be part of the information pyramid. So I'm not going to necessarily dwell on every aspect of data. I expect you all to be reading this. Obviously, you know the difference between bits and bytes, and now we've gotten up to yottabytes. And again, it's just going to continue to accelerate. Structured data, again, means that it could be stored in a relational database or a spreadsheet. And it would be things that could include name, age, gender, cholesterol results. It could be categorical or numerical. Unstructured is all too common in medicine, as you well know. It could be free text. It could be a discharge summary. It could be a radiology note, if you will. Semi-structured is a little bit different yet. And the two examples I give would be an XML document or JSON that has some structure and unstructured at the same time. And we've talked about data being messy and the problems related to it. There are plenty, such as it being so largely unstructured. There are lots of HIPAA concerns, clearly, and it's often unclear to me why we can get NHANES data. Of course, it doesn't have any names or addresses. It doesn't have regions, but you have good NHANES data that's readily available to download that I don't see in the literature very often, whereas I see MIMIC3 data in the literature all the time. That's, to me, perplexing because this is at the patient level. You don't need to have any research training and pass a CITI test, CIT test. So that's why I've created a database just using NHANES data. It's extremely valuable, but no question that HIPAA has become one of the greatest obstacles to freely exchange data there is. And then what we have said in some of the workshop, the board review courses, that's disconcerting is it looks like now they can tell gender, age, and maybe race from x-rays and retinal photographs. Will we see a time where now we've got to worry about AI images identifying an actual patient? So that may add to the concern and heartburn. Most of the publicly available data sets are small. In fact, the ones I use are small by and large. The NHANES data is 5,000 patients, so that's a much greater size. They're really overly clean, and that tends to give you overly optimistic results. It's not typical of real world data. I do have a data set called Messy Data that I've not posted, but maybe I'll put that on GitHub. I'll figure out how to do that. So it has missing data, acronyms, as you know, medical docs love to shorten their dictation by using to use acronyms, and they're different in different facilities. There are also multiple data standards, and supposedly DICOM is not 100% specific. DICOM can vary slightly, adds to the confusion. And so, again, we've got a ways to go. We've made more progress, in my opinion, with image analytics than we have with natural language processing. I mean, transformers have done a great deal to generate and understand text, but I haven't seen it applied to healthcare in any way that's earth-shaking or will save time for the average doctor. Probably around the corner they will, but right now I've not seen that very much. Also, as you well know, data tends to be siloed. Different areas, you may be stuck with claims data, which has all kinds of problems associated with it. Like it may just say rule out MI. That's really not a diagnosis you can do much with. So in any case, you may have data in all kinds of places and all kinds of formats, which interferes with it. And most of us are not ready to deal truly with big data. whereas the data scientist and data engineer are really capable of doing that. I remind people that data scientists and statisticians don't use the same terms. It's wise to look at this for a while and try to understand that these are what you're stuck with when you talk about outcome or output. Actually, I don't see output listed here, it probably should be. That you just have to learn that they mean the same things. And that you'll see them depending on who wrote the book that you saw or the video, they may use different terms. And then even when you go to say, I hope you all have visited the University of California Irvine Data Repository. You can't download all the data easily, and some of the data is old, it can be messy. Sometimes it doesn't have a good data dictionary, so that's the challenge. All right, looking at some of these tables, this is the standard way when you look at data to divide it into quantitative and qualitative. So under quantitative, discrete, meaning whole numbers that can't be broken down, you never say that I have 1.5 children, for instance. Continuous would be something like height or heart rate. Qualitative is non-numerical data that's categorical, such as benign and malignant. Ordinal has order to it, you know, small, medium, large, as just an example, or it could be an echocardiogram of normal, borderline, and abnormal as an example. And then interval and ratio, I'm not really going to go over. But one thing that adds a little bit of confusion is very common as an outcome to label the outcome instead of, let's say, benign and malignant, to label malignant as 1 and benign as 0. That's traditional to label the category that you're interested in as 1 and the other category is 0. And although that's a number 1 and 0, it's considered discrete. So I know that creates a little confusion. You'd look at 1 and 0 and say that's continuous or numerical, but it's considered discrete, and computers love 1s and 0s. So when you look at programming, I'm sure you all are familiar with the difference between integers, floats, characters, strings, and Boolean. I won't belabor that. The other thing is, as you get further and we talk about particularly AI, where you're going to basically you're going to vectorize images and vectorize paragraphs, what you're doing is converting those into a matrix and vectors, and then you can apply matrix multiplication and other higher math using linear algebra to calculate distances between rows and columns, and even the angle using cosine similarity as an example. But so that's scalar, a row vector, a column vector, matrix, and then a tensor is 3-dimensional, which is critical when you're doing image analysis as an example. So those terms are important to understand the difference and understand this is why linear algebra is so important for artificial intelligence. This is a story, Lego data story that Flora shared with me. And it's just basically what happens to data, but I also threw in here that the fact in medicine, when we come up with a data science project, we would hope it's not just a proof of concept to something where you get a quick article and you're done. You never bother to implement it or really test it. We would hope that the goal, the holy grail, would be to improve patient outcomes, reduce cost, improve the patient experience, improve the clinician experience, and improve health equity. So here's just an example of taking data like Legos, sorting them in this case, arranging them, if you will, into categories, presenting them visually, explaining the story, and then doing something useful with them. So I think that is really what we're attempting to do. Now, let me stop there and see if there are any questions about any of this in terms of how you start off thinking about data. or discussion about any aspect that, you know, is applicable to your job, let's say. If not, I see something, let me see. No questions so far, okay. Now understand, even here, some of the terms are confusing. Data wrangling and data munging, M-U-N-G-I-G, is basically the same thing. And really what it kind of means is cleaning up the data. But you'll see, you know, data preparation, data cleaning. I wouldn't worry too much about the terms, other than simply say there are some logical steps early on. First of all, what is the format? You may have to clean it up. What are you going to do with dates in different formats? And often missing data could be blank. There could be a 0. It could be a question mark, or NaN standing for not a number. There's lots of different things that are not uniform, how latitude, longitude is reported, so forth and so on. So the first thing you do, we're going to look at that, maybe in a spreadsheet, and try to make sense out of it. And now I'm not going to talk about data validation, but Microsoft Excel can actually do some data validation to help you. The figure 2.5 just shows you an example of this. I think this came from my file that I call messy data. You see the percent sign, that's, you know, won't compute. You see the less than, that won't compute. You have to get rid of. You have to decide, what do you want to do with n/a? So automatically you've got issues here. Let's see, you got, I don't think there's any blank ones, but you'll run into plenty of blank cells in any spreadsheet. Now, feature engineering is a big term, and other people refer to it differently. Often it means that you're going to combine features, you're going to take away features, you're going to add features, you're going to calculate on features, you're going to handle missing data in there with imputation or deletion. And this is a whole major topic, because if you do it poorly, you're in trouble from day one. And I will say that in general, when an early thing you do is to split your data into training and test, you're going to leave that test data alone. And I want to just make that clear to you. And then you're going to work on the training data. And we can start. Dave, you want to contribute to the missing data part? You did a nice section down here later on imputation, if you will.
Yeah, let's stop for a second. There was a question. There was a John raised his hand, so I think he might have a question. John?
Okay,
Yeah,
John.
well, not necessarily a question, but just something to point out as a to add some specifics to some of the things that you're talking about. Can you go back to Orange and that cardiovascular
To the workflow
example?
or?
Yeah, to the output where you had all the different features contributing to whatever
To the
prediction,
rank?
to the rank, yeah.
Okay.
So just here, like the data, like chest pain, what, you know, that's a question of, I mean, max heart rate is something that's pretty easy to define, but how do you define chest pain? Where is the provenance of where does that particular data feature come from? That sort of thing is really important. And without knowing that and doing some of the wrangling and foundational work initially, a lot of what you're coming up with is really difficult to interpret and may have different outputs depending on how you actually curate and have the provenance of that particular data feature.
Okay, but let's expand that a little bit, and I appreciate your comment, because I don't want to take anything for granted in that regard. So let's go back and look at this. Notice there's a number 3 to thallium and 4 to chest pain and 2 to exercised angina. Why is it's categorical data? Notice it's green. like 2 would be female, as I recall, not male. But the point is, so then, to your point, John, you'd create a data table and look at the different kinds of chest pain and actually,
So my point in this is the source of that data, of those pieces of data, from a clinician clicking a discrete item on their documentation? Is it from somebody who is abstracting that and essentially normalizing some discrete and maybe non-discrete textual data? And, you know, and if it's, say, the former, where the physicians are being tasked with clicking some discrete item, how good is that data? Because you're now adding an extra piece of workflow to the clinician, and a lot of them may say, I'm not going to do this, I'm just going to document it as text.
well, first of all, I always pull the original article to see exactly how it was done, okay? I mean, that's number one. So these were roughly 500 patients from several, Cleveland Clinic, something in Switzerland or whatnot, where every patient got cardiac catheterization. They all got treadmills, including a thallium stress test. And all of this was reported out of that.
So I'm not talking about this specific example. I'm talking about
Okay.
in general, and especially when you're talking to clinicians. And if you say chest pain, they don't necessarily understand all these sorts of machinations that I just talked about. They just think, well, chest pain magically appears as a data feature, and I can rely upon that. But what we have to understand is that there's chest pain in one circumstance that may mean something different in another circumstance, or that the reliability and the purity of that data may be different in one circumstance versus another.
Well, there's no question, and we've said all along that you can get in a garbage in, garbage out situation if you don't know the origin or the definition. And that's why, again, pulling the original article, looking at a data dictionary, all those things are critical. So this is just an educational example. One of my areas of heartburn here, one, even pulling the original study, I don't know if any of these people were on statins. So so that affects their cholesterol greatly. Number two, most of the people with heart disease were labeled as asymptomatic when it came to chest pain. That doesn't make sense to me. You know what I mean? So to your point, again, I'm using this for education, but if you really wanted to use this as a model for cardiologists, you'd have to answer that question. You would have to know, what did they mean by asymptomatic? They talking about before they had the stress test? I think clearly not during the stress test, but I can't answer that, even pulling the original article. So, point well taken. So this is, again, largely just education, though.
Yeah,
But
John
again,
brings up.
Correct.
John brings
I
up
just
a-
wanted, I just wanted to create a very applicable example of some of the stuff that you're talking about right now.
Yeah, but you're no
just to
question,
hammer that point home.
your model is only as good as your data. And that's why this chapter's long, laborious, is we will attempt as many ways as possible to show you the things you need to do to get your data ready before you ever get to the modeling phase. David, you want to continue on with that missing data?
Yeah, sure. Just as another comment of, John's great observation, if you look at the world of Lean Six Sigma, for example, there is incredible focus on being able to define the problem and measure the data correctly. And there's a whole section of, measurement system analysis and making sure that you collect the data that's going to make sense for everybody, in this case, the clinicians and the analysts downstream. And so that's a huge topic as you try to get into a research project or problem solving project. So, good point, John. So back to the missing data part here. when we get into feature engineering and data wrangling, as Bob mentioned before, that takes up the vast majority of the time of very serious data analysts and data scientists. They spend the majority of their time in that area and they don't get much credit for it because people are just breathing down their neck. When am I going to get my predictive algorithm? But you know, they roll their eyes and they know they got to go through this, spend the 75–80% of their time on this upfront part and analyzing and completing that section very carefully. Actually, at Nova University, starting in January, I created a class a year and a half ago for Nova University, the College of Osteopathic Medicine, called data wrangling. And it took a year and a half for them to, we're going to finally roll it out starting in January. I mean, a whole class just on that one topic. And it's a topic that a lot of analysts love to avoid because it's very inconvenient. And this topic here that Bob had just rolled up to, missing data. Okay, people look at, oh, missing data, inconvenient. I might just delete it. I might just ignore it. There is an entire science about how you deal with missing data. On top of that whole thing, you have to also analyze, if I have missing data, is it completely at random? Is it missing at random, which is very similar to the one I just mentioned, MCAR and MAR, and then not missing at random. Data that's not missing at random is very destructive to a model. And if a certain data is not missing because people do not want to disclose that information, that might be very pertinent to the predictive model. And you might say to yourself, well, how in the world am I supposed to know if my missing not at random is not at random? How in the world would I know it? It's missing. Well, thanks to statistics, we could actually compare the missing data compared to the non-missing data and use hypothesis testing and see if there is a difference numerically and statistically between the missing data and a non-missing data for each of the individual columns or features that we're looking at. And then if we find out that it's not missing at random, which means that, hey, I get a p-value below 0.05 and something's very mysterious about that data, then I got to go back and ask the validity of that whole situation. So there are so many considerations that start here just with something simple. Oh, missing data. Okay, let's just, you have different options. And I saw a very interesting article that was published on the internet. How do people typically how do they typically deal with missing data? And guess what the most popular topic is? It is to just delete all the rows. Delete all the rows that have any missing data. That is the absolute most popular topic. Well, again, if you don't know if it's missing at random or not, first of all, you're blowing away, valuable data, and then you're blowing away data that might be, not missing at random, and not knowing that will influence your entire outcome. So it's a very tricky and sticky topic that is overlooked and should not be overlooked. And we talk about that here. And then as you scroll down further, Bob, we get into the whole topic of how do you deal with missing data, then the whole topic of imputation. Bob, do you want to give an intro on that, or do you want me to just continue on with my soapbox?
Sure. And again, imputation, it really just means how are you going to handle missing data? Are you going to replace it with a value? And then there's a lot of different ways to do it that we're going to discuss. And then we use the orange impute widget. And David, I'll let you just keep describing that.
Okay. Now, when people hear the word imputation and then when they find out what it actually means, it means that I'm taking a missing data point and putting in a value for it. It kind of brings back memories of people when they've read stories about lying with statistics. That's the first thing that comes to mind for people. And they wonder, oh my goodness, what's actually happening here? Now, what's really interesting on that whole topic is you know, if you, again, you look at, like I mentioned, there's an interesting article of what are the most common ways for dealing with data imputation. Well, what the most popular method is actually people would take the average of an entire data set for that column. And it'll say, if I get a missing data point, I'm just going to throw in the average. And that has advantages and it has some big disadvantages. And we talk through that in this section. And fortunately, there is a whole variety of different sections. If you want to keep on scrolling down, Bob, a little bit, we have a lot of different options. You scroll just a little bit at that point, a little bit higher. We have different options here for how to deal with imputation. Here we see in orange a certain widget that allows us in the pre-processing. We could just say, okay, don't impute. Average, impute. Now just imagine if half of your data is missing and I throw in the average value for all the missing data, guess what your histogram of that data is going to look like? It's going to have a huge spike in the middle because I took all the missing data and I turned it into, you know, an average. And there's other methods. And this whole section goes meticulously through the pros and cons of these sections. And if you scroll down a little bit further, what I actually did for this section is actually took a perfectly fine data set with no missing data and randomly created some deletions. And then, so here in that situation, there was 390 rows of patient data, by the way. So randomly took out 20% of the data for, you know, a variety of the 12 of the predictors and said, all right, now let's use these data imputation methods and see which one actually gets us back to what the data looked like before I randomly and maliciously tore out 20% of the data. And if you read through this section in detail, and if you actually follow that type of exercise, you will then hopefully get a little bit of a feeling and a little bit of a comfort level of what imputation is actually doing. Now, you know, if you like in this situation here, if you have, for example, the top 3 predictors here for this diabetes data set was, you know, we had glucose, age, and then we had systemic blood pressure. And then what I did is on the far left, you could see that's what the data looked like, you know, where there was nothing missing. It was 390 data points. We got it was a legitimate data. The next row to the right randomly took out 20% of the data. And since it was taken out randomly, we could see that the distributions or the histogram shapes are very similar to the before data, before nothing was taken out. Now, if we say, all right, I'm going to impute, now I look at some of the imputation methods. And if I start to say, all right, I'm going to impute with random values. And if you scroll down a little bit more to the bottom, what you see is these columns are kind of green, yellow, or red. And if you could scroll a little bit back up, Bob, again, you know, then I get over to the imputed random value. Now, when I imputed the random value and you compare that to the original data, you don't see much of a difference. You say, okay, all right, that's not bad. And now you say, how is that even possible? Well, this option in orange not only put in random data, but it put in random data that matched proportionally the curve or the distribution shape of that data. Now, if you go to one column more to the right, now it imputed values based on what's called a model-based imputer for all missing values. And that one didn't look too bad either. But if you look to the far right, and again, on the internet, this is the most famous way, the most common type of term that is used for dealing with missing data. Oh, let's just throw in the average for the whole data set. How bad could that be? Well, guess what? That might be good for the predictive model. When I say might be, you know, what it's going to do, depending on how much missing data you have, it's going to skew the model, make it look less variable. But if you do data visualizations like we did here with the histogram, you'll see that you get this huge spike. And this was only when 20% of the data was missing. So when you're imputing data, if you use certain methods carefully, you could actually emulate the data as if it was, if you knew what it looked like before it was missing, you could get very close to what that looks like. But putting in a fixed value, let it be the mean or the median or something else, you could, like I said, you could maybe make the predictive model happy, but good luck in trying to explain your data visualizations to anybody after you've imputed a fair amount of data with a fixed value.
Okay, what I may do, we've now at the 1 hour point, and that seems to be when people want to call it. What we're gonna do is send you an updated chapter 2. We'll pick it up again in the same section on missing data and carry forward, we'll work forward in terms of how do you handle that, and talking about outliers will follow. David has some very interesting plots and diagrams here to show that. So I think we'll close it here. I will record this. I will post it on the YouTube channel and make that available to everybody. But I think this is a logical stopping point to say that we'll take it up and continue our discussion about missing data. Any other questions before we close? See one in chat. Crude oil that people don't want to share.
Yes, that's another good quote.
Yeah.
Raw crude oil, nobody wants to share.
Okay, otherwise, hope you have a good weekend, and I'll send out a notice. It'll again be the 3rd Saturday of the month in November. So everybody take care, and we look forward to further discussion.
Okay, thanks, everybody.
Thank you, both David and Bob, for being so dedicated on Saturday morning. Thank you.